Hello everyone. Today we're going to introduce magnetoresistive random access memory, which is widely known as MRAM. This is our outline. We will first have an introduction to MRAM, then go through the MTJ, STT, and SOT, which will be introduced in detail later. First, you might wonder, what is RAM? RAM, standing for Random Access Memory, is one of the most fundamental elements of computing. It is a form of computer memory that can be read and changed in any order, typically used to store working data and machine code. So what is RAM used for then? It's very fast, which makes it ideal for things the computer is actively working on, such as applications that are currently running, and the data those applications work on with. It can help to think about RAM with the analogy of a physical desktop, your working space, where you scribble on something immediately, is the top of the desk, where you want everything within arm's reach and you want to no delay in finding anything. That's RAM. In contrast, if you want to keep anything to work on later, you put it into a desk drawer, or store it on a hard disk, either locally or in the cloud. In short, RAM is used for any task that requires fast access to computing resources. After realizing the random access memory, let's talk about magnetoresistive random access memory, which is widely known as MRAM. MRAM is a high-speed non-volatile memory that can provide unique solutions which improve overall system performance in a variety of areas, including data storage, industrial controls, networking, and others. A series of scientific discoveries and innovations have stimulated progress in MRAM technology and commercial investment worldwide since the late 1990s. It is the method of writing the magnetic state of the storage device that distinguishes one technology generation from another. MRAM technology can be classified by the switching method employed to write data. There are three generations of the development. First generation MRAM is generally understood to include methods using magnetic fields to program the array. Toggle MRAM is the only first generation MRAM in mass production. A strong advantage of field switching is unlimited write endurance, since reversing the free layer magnetization with a magnetic field does not create any wear-out effects. A disadvantage is the difficulty in scaling to smaller sizes, due to several factors including the magnitude of the required switching current and a somewhat complex memory cell geometry. Second generation MRAM uses STT to program the array. STT switching can be accomplished with reasonable efficiency with MTJ devices having either in-plane or perpendicular to the plane magnetization. STT MRAM with in-plane devices began commercial production in 2015 with a 64 million bits product and is expected to ramp to volume production in 2016 with a 256 million bits product. STT MRAM with perpendicular MTJ devices is under intensive development at a number of companies around the world. A number of physical phenomena are under investigation for use in third generation MRAM, including voltage-controlled anisotropy, voltage-controlled magnetism, spin Hall effect, and spin-orbit torque switching. The potential for improved MRAM scaling and performance comes from the idea that switching could be accomplished while passing little or no electrical current through the MTJ device. However, each effect has challenges to overcome for use in practical MRAM circuits. Some examples of those challenges are as follows. Voltage-controlled anisotropy does not directly lead to deterministic switching between two stable states. but is more likely to be applied in combination with another innovation for use in an MRAM array. Reliability issues like wear-out and parameter drift needs to be better understood for practical voltage-controlled magnetism devices. Spin Hall effect does not lend itself to efficient switching in devices with perpendicular magnetization, and spin orbit torque switching appears to require innovation in materials to increase the magnitude of the effect for improved switching efficiency. Possible practical application of the MRAM includes virtually every device that it has some type of memory inside, such as aerospace and military systems, digital cameras, notebooks, smart cards, mobile telephones, etc.
For this part, I am going to introduce the magnetic tunnel junction, which is a basis unit of MRAM. Firstly, I want to introduce what is a RAM. RAM contains billions of tiny plates called capacitors that hold electrons. To store the information, computers send a current of electrons into the capacitors. Some of these electrons collect on the plate. If the number of electrons on the capacitors is above a threshold, the computer assigns it a value of 1. Otherwise, it is a 0. Unique patterns of zeros and ones encode information like letters, numbers, and images. As chips get smaller, we must face the problem of charge leakage. When the electrons count falls below the threshold, the stored data is lost. So we require more and more power to keep the threshold as chips shrink. Fortunately, an emerging technology called spintronics could solve this problem. Spintronics use spins, another property of electrons, to encode the data into the computers. The spin of an electron is either up or down. It is helpful to think of the spin-up electrons as little magnets, with their north poles pointing up, and spin-down electrons with downwards pointing north poles. And data is stored based on the spin states of electrons that are already present now. This means that there is no problem of leakage with spintronics. Once information is stored, it stays there until we want to change it. The spin states of electrons change if we give the external magnetic field. To take advantage of this, scientists developed magnetoresistive RAM, which replaces capacitors with magnetic tunnel junction. A magnetic tunnel junction is a basis unit of MRAM. Magnetic tunnel junction is made up of an insulator sandwiched between two ferromagnetic materials. An insulator is a kind of materials with very high resistivity, which means the electrons are very unlikely to move towards it. A ferromagnet is a material in which the spins tend to align along the same direction. And in the magnetic tunnel junction structure, the bottom one is pinned by external force, and the upper one is called free layer, whose electrons changes their spins in response to external magnetic field. When the spins of the ferromagnetic layers are parallel, the structure stores as 1. Opposite spins represent as 0. To read the data and determine whether it is a 0 or a 1, the computer sends a tiny current through the structure. If the spins of the top and bottom layers are parallel, the electrons can tunnel through the insulator. If the spins are opposite, almost no electrons can tunnel through the insulator. By seeing how much current reaches the other side, a computer can tell us whether the magnetic tunnel junction structure is holding a 1 or a 0 signal. As shown on the slides, this structure is a famous example of magnetic tunnel junction. There is an MgO insulator sandwiched between two ferromagnetic materials, and there is cobalt iron boron. And we can see that when the spin is parallel, the recording signal will be 1. And the right hand side, there is an anti-parallel, which means opposite spins. So this signal will be 0. However, due to the local thermal disturbance, the coercivity of magnetic layers may be reduced significantly, and the effect will relate to the deviation of switching when the magnetic tunnel junction is weak. In order to solve this problem of thermal disturbance, we can turn to use perpendicular magnetic anisotropic. And there is an example for that. When the spin is tend to align on the same direction, and the signal will be 0. However, if there is opposite direction, and the signal will become 1.
In this part, we are now going to use simple semi-classical mechanism to illustrate how spin flip. We've seen that ferromagnet can allow majority carrier paths as a spin filter. It will cause an itinerant magnetization gradient, both sides of this scheme. Capital M is magnetization for magnetized ferromagnet. Lowercase m is magnetic moment for free carrier. And we can see that the magnetization for the free carrier is a gradient distribution. And it is definitely that capital M will be forced by magnetic field from itinerant carrier. It is reasonable that the magnetic field is proportional to the itinerant magnetization. And only perpendicular component of delta M can cause torque to flip local magnetic moment because M0 is equilibrium magnetization. It means that M0 is parallel to the capital M. And only perpendicular component can cause torque. So we can separate the delta M perpendicular to two components, and we substitute this term into this equation. We can get that torque can be separated into two components. First one is damping torque. The second one is field torque. For the damping torque, it means that like this. If lowercase m is in this direction and the capital M is in this direction, the angular momentum is transferred to local magnetization capital M. So the capital M will rotate with respect to a specific angle. And for the field torque, this will make the capital M to do a precision motion along its direction, like this. Okay, so how angular momentum or spin angular momentum transferred to local magnetization is approximately, of course, it is a very simple model, but it can help us to imagine how the capital M rotate. So we've seen how ferromagnetic magnetization rotate. STT and MRAM, like this figure, uses spin angular momentum from current to flip the free layer of MTJ. So it does not depend on external field. It means that it can accurately flip specific cell in device. And it saves a lot of space, so can improve cell density of memory. However, the writing current is not symmetry. It means that the current drive magnetization up or down is different. In addition, writing and reading use same path might cause some error either. And here I show you why the current for writing is not symmetry. First, we consider parallel state. And now, if we want to change, it means that we want to write some information in this MTJ. So we want flip this magnetization. We can input a current into this MTJ, and the majority carrier will pass the pin layer, and the minority carrier will be reflected, and this minority carrier will transfer its torque to the free layer. So the free layer will be flipped. This is P to AP, anti-parallel. It uses the minority carrier. And now, if we want to make the AP to P, we input and current in this direction, and then the majority carrier will pass through, and the minority will be reflected. So this majority carrier will exert torque to the magnetization, and it will flip to the up state. So the AP to P use the majority carrier. It is why that writing current is not symmetry. It means that we need a larger transistor. To accompany with this device. Okay, so the next is SOT and RAM. Before we discuss what is spin opto torque, let's see how SOT and RAM works. As this figure, different from STT and RAM, writing and reading path is different now. Most interesting feature is writing current do not have to across my point. Do not have to across the MTJ. So for SOT device, writing current is symmetry, but it needs two resistors. It reduces the cell's density in the memory. So now, let's see a famous spin opto coupling. We use this semi-classical model to show how spin and opto interact. As we know, electron revolve around the nucleus. However, if we write on electron, we might think nucleus would rotate around the electron. So, electron in its reference frame will feel a magnetic field from nucleus motion, and the energy of magnetic moment is, we know, is mu dot B. Energy is mu dot B. So electron has spin up and spin down. So it will have different energy. Depends on it is parallel to orbital angular momentum, or anti-parallel to the orbital angular momentum. So you can see that for anti-parallel angular momentum, because the total angular momentum is less, and this is it is the orbital angular momentum plus the spin angular momentum. So this one will have more energy, and this one will have less energy. And what I want to say here is SOT is actually a relativistic effect. For electron, it will feel a magnetic field, and the field will interact with its spin. Another famous experiment is Stern-Glach experiment. In this experiment, we see that how magnetic moment forced in a non-uniform field, and then this spin down, spin up and spin down state will be separated to both sides. In this is our material. We can imagine that if we write an electron and we go through this material, the electric field from nucleus will cause a magnetic field gradient in electron's reference frame. And a Stern-Glach experiment, the gradient, the non-uniform magnetic field will cause, will have a force interact with its spin. So the spin will, so the different spin will be separate to both sides. MRAM. Finally, we can imagine that current passed through IW layer will be separate to both sides, like maybe spin up will accumulate on top layer, and spin down will accumulate it on the bottom layer. So this top layer spin will make torque to flip the free layer, and so the magnetization will be changed. Bye.